Algebra 2, Section 11.1, Mathematical Patterns. Start with an example. It says start with a square with sides 1 unit long. On the right side, add on a square of the same size. Continue adding one square at a time in this way, and to draw the first 4 figures of the pattern. Okay, so that would look like this. First pattern is a square. The second pattern is a square with another square tacked onto it using one of the sides. The third pattern would look like this. The fourth pattern would look like this. Okay. Now the point to that is in the next 2 questions. It says write the number of 1 unit segments in each figure above as a sequence. Okay, so there were 4 segments. And then there, count them if you need to, there are 7, and then there are 10, and then this one there are 13. Okay? And with that, you could look at this and probably most of you pretty quickly could discern that the next number is going to be 16. And that's what part C says here, predict the next term in the sequence. And the reason is because these are going up by 3. 4 to 7 to 10 to 13 is add 3, add 3, add 3. So the next term would be add 3. That's how you're going to get 16. In doing so, what you've done is you've recognized a pattern, a mathematical pattern. Now, this particular one is what's known as an arithmetic sequence. And what's coming in the rest of this chapter is section 11.2 will deal specifically with arithmetic sequences. Section 11.3 will deal with specifically geometric sequences. And then 11.4 and 11.5 will deal with something called a series. 11.4 is arithmetic series. 11.5 is geometric series. We'll define those when we get here. Right now in 11.1, this is just somewhat of an overview of these 2 types of sequences, arithmetic and geometric. And 4, 7, 10, 13 is an example of an arithmetic sequence because of the fact that it goes up by the same number. Now, I will point out that this is not as simple as 1, 2, 3, 4, 5. You see, 1, 2, 3, 4, 5 is also an arithmetic sequence, but it's simpler. And, for the same, 2, 4, 6, 8, 10, or even 5, 10, 15, 20. These are numbers or sequences that not only go up by the same number, but they also have a first term that is that number, right? 2, 4, 6, 8, 10. The first term is 2, and it's going up by 2. For that reason, I would consider 4, 7, 10, 13 to be slightly more complicated than that. The first term is 4. The next term is 3 more than that, and then 3 more than that, and then 3 more than that. And 16 then is 3 more than that. This is an arithmetic sequence. So here would be the notes for today. Defining what a sequence is, it's simply an ordered list of numbers. And there are 2 types of sequences, 2 common types. They are arithmetic and geometric. Arithmetic sequences and geometric sequences. Now, you should know that for the homework in 11.1, there is a third option, and that option would be neither. Okay? In 11.2, we'll get really specific with arithmetic sequences. In 11.3, we'll get really specific with geometric sequences. But for right now, maybe you could fit it into one of these 2 categories. And if not, well, then it's a possibility that can happen. It's a possibility that it's neither one. For example, it could be quadratic, right? Or some other pattern. And you'll still be able to do as the first example that we just did. You'll be able to do that in these examples in the homework, but it just may not fit into the category of arithmetic or geometric. Okay, but there are 2 common types, and I want to cover them both. And not only are there 2 common types, there are also 2 common ways that we can express each one. Okay, so here I give you an example, 7, 15, 23, 31. If you investigate that, you'll see that those are going up by 8. Okay, now quick side note, they don't have to go up. They could go down to be an arithmetic sequence. 10, 8, 6, 4, 2, 0, negative 2. That's an arithmetic sequence as well. It's going down by the same number. But this one's going up by 8. And to predict the next number, if you wanted to know what the 5th term is, you just add 8 to it. Okay, now here's a critically important thing for you to understand. 7 is the first term, and it has a name, if you will, that's called A sub 1. This is A with a subscript number 1. That's what I think of it like it's its name. Its value is 7. It's the first number, therefore its name is A sub 1. Sometimes I say A1, sometimes I say A sub 1, subscript 1. The second term, A sub 2, is 15. 23 is the third term, it's called A sub 3. 31 is the fourth term, it's called A sub 4. If I could find A sub 5, which I could, it would be 43. The value would be 40, excuse me, it would be 39. It would be 39, and the value, its name would be A sub 5. 39 A sub 5. The next one would be 47. Its name would be A sub 6. Geometric sequences are not this way. Geometric sequences, and again, you could probably just look at this list and see what's going on with this. You know, to get from 2 to 6, you could add 4, but adding 4 would not give you 18. Instead, this is a multiplier of 3. Okay? So 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54. If you wanted the next term, you could multiply by 3. They still have the same naming system: A1, A2, A3, A4. Okay? Now watch this. On your calculator, let's go back to the arithmetic. You could go 7 plus 8, and that would be 15. And then if you go plus 8, it'll give you yet the third term. And in doing so, what you've done is you've basically trained your calculator to do this pattern of adding 8. And I now will only press enter, and it'll give me the next number. That's A sub 4. Now suppose I asked you for A sub 9. One quick way to get there, because we're already at A sub 4, would be to hit enter 5 more times. There's A sub 5, 6, 7, 8, 9. 71 would be that number, and I'm calculating this in what's known as a recursive way. This is when you add the common difference to the previous term, it's known as recursive. Okay, so out here somewhere would be A sub 9, and that number, whatever it was on my calculator, would be what it is. Okay, now to express a recursive formula, you always need at least 2 lines, and in Algebra 2 it will always be exactly 2 lines. You want to say what the first term is, and then you want to say what every other term is based on the previous term. Okay, now here's the most challenging part of the next 3 lessons. You understand this. This will probably go pretty well for you, these next 3 lessons. You need to realize that A sub n being the current term, A sub n minus 1 is 1 term previous. Okay, this means the previous term. Let me block that up in red. This right here means the previous term. Okay, and A sub n being the current term, A sub n minus 1 being the previous term, what I do to get the current term is I take the previous term and add 8 to it. For this example, the specific 7, 15, 23, 31, where you're adding 8 to get the next number, I take the previous term, which I have in a red block, and I add it to 8. Okay? Now, why is this the previous term? Well, because n minus 1 will give you 1 less number. So, for example, if this is A sub 5, n is 5. If I plug 5 in here for n, 5 minus 1 is 4. So to find A sub 5, I take A sub 4, which is what's in the red rectangle here, and I add it to 8. Okay, but don't I know what A sub 4 is? It's 31. So to find A sub 5, I take A sub 4, which is 31, and I plug that in for the red box. 31 plus 8 would give me the 39. Now there's a limitation to this, isn't there? What if I asked you for the 57th term? Well, you can't have the 57th term, right? So you're talking about A sub 57. You can't have that unless you know A sub 56. Again, A sub 57 minus 1 would be A sub 56. Okay? So there are limitations to recursive, but this is the way that you show it anyway, with 2 lines. Some textbooks use that bracket. I think ours does not use that, but it does kind of link those together. All right, let's do the same thing for geometric. A sub 1 is 2. A sub n, how do we get A sub n? Well, what we do is we take the previous term and we multiply it by 3. So A sub n is equal to 3 times A sub n minus 1. And again, what I'm trying to emphasize more than anything else is you must realize is that that means the previous term. A sub n minus 1 is not some elaborate calculation. It's just the previous term. 3 times the previous term. I want to know A sub 5. Plug 54 into the red box. 3 times 54 would give me the number that would go right here. Okay, now let me show you too on the calculator. We can do that as well. 2, 6, 18, 54. How do I get from 2 to 6? Well, 2 times 3 is 6. Times 3 would give me the third term. What did I do? Let's try that again. 2 times 3 is 6. Times 3 gives me 18. And then just enter gives me 54. Enter would give me a sub 5. Here's a sub 6. Here's a sub 7. Notice that those numbers are climbing a lot faster as I do this, right? That's the nature of geometric sequence. This is a geometric sequence. All right, now let's back up and let's talk about 7, 15, 23, 31 again. And basically, recursive formulas are limited, right? What if I wanted to know, the 112th term, the 5,000th term, etc.? You would not want to calculate that recursively even if you had the use of your calculator, because you'd have to hit that enter button like 5,000 times, okay? So there is a better way, and that looks like this. A sub n is equal to the first term. Now, if you don't get this exactly, that's going to be okay, because again, we'll get more into arithmetic sequences in section 11 too. But just try to comprehend this for what it's worth. The first term plus 8 times n minus 1. See, we're going up by 8 a certain number of times. How many times? Well, n minus 1 times, because the first term, you're not going up by 8 at all. The second term, you're going up by 8 one time. 2 minus 1 is 1. 8 times 1 is 8. And 7 plus 8 is 15. That would produce the 15. If you want to check it right now, plug a 2 in for n in both places. This is a sub 2. Plug a 2 in here and see if you don't get 15 as an output. Remember that a sub 5 was 39. Plug a 5 in for n. That means you're calculating a sub 5. Plug a 5 in for n. 5 minus 1 would be 4. 4 times 8 is 32. Plus 7 would give you 39. And for that matter, go ahead and plug in a 57 or 198, whatever number. And by just one simple calculation, you can find any number of term in the sequence. I want to know the 198th term. I'm finding a sub 198 by plugging 198 in here for n, and then you would just do the math. 198 minus 1, take that number times 8, take that number plus 7, that'll give you that. The explicit formula for geometric has its own little thing, and the first term is 2, and what are you doing? You're multiplying that number by 3 a certain number of times, okay? And it's to the n minus 1. And again, we'll get more into geometric sequences and why it's n minus 1, and it's not just to the n. It's basically exponential, but you do need to increment that n down 1, and that's something we can talk more about, or you'll comprehend better in section 11.3. Okay? So again, as sort of your completed notes here, this is the recursive formula for arithmetic. This is the explicit formula for the arithmetic. The specific sequence 7, 15, 23, 31. This is the recursive formula for 2, 6, 18, 54. This is the explicit formula for the same sequence. Okay? Now, one more example. This says, suppose you drop a ball from a height of 100 centimeters. It bounces back to 80% of its previous height. How high will it go after its fifth bounce? Okay, now let's do some simple math on that. The first number would be 100. If it drops and bounces back up to 80% of its previous height, 0.8 of 100, 0.8 times 100 would give you 80, right? The next number would be 64. 80 times 0.8 would be 64. And the reason I paused there is I was setting up the geometric sequence on my calculator, my handheld, so that the next number will be 51.2. And the next number will be 40.96. Okay, now let's stop there. Does that answer the question? Suppose you drop a ball from a height of 100 centimeters. It bounces back to 80% of its previous height. How high will it be after its fifth bounce? Is that the answer, 40.96? No, that's not the answer, because 100 was not after any bounces. 80 is after the first bounce. This is the second bounce. This is the third bounce. This is the fourth bounce. We'd have to do this one more time, and that number is 32.768. Okay, now I want to be really clear about this. This still has a name, and it's called A1. This one is A2. This one is A3. 51.2 is A4. This one is A5. And our answer is A6. The sixth number is actually after the fifth bounce. Okay? Now, to close this up, let's go ahead and calculate, or not calculate, let's go ahead and write out the recursive formula and the explicit formula for this example. The recursive formula would look like this. A sub 1 is equal to 100. A sub n is equal to 0.8 times the previous term. 0.8 times a sub n minus 1. Now, pardon my handwriting, it's imperfect, but this is 0.8 right here. This is the times dot. You don't need the times dot, but I included it. That's the recursive formula for this situation. And I just did this on my calculator because I wanted each term. I took 100 times 0.8 gives me this, times 0.8 gives me this, times 0.8 times 0.8 times 0.8 gave me the answer. Explicit would be better if we can write it. And that is a sub n is equal to 100 times 0.8 to the n minus 1. And just before we're done here, I'd just like to test that. We wanted after the fifth bounce, so we wanted the sixth number. If I plug a 6 in here for n, and I just do this number on my calculator, do this calculation, I go 100 times 0.8 to the fifth, right? 6 minus 1 is 5. I do, in fact, get 32.768. Okay, so that should be enough for you to do the lesson. Again, remember that there is the possibility that it will neither be arithmetic or geometric. And if that's the case, just try to answer the question as you can. A lot of them will fit into one of these two categories. Thanks for tuning in.